this will go to 4th period as well. So kind of some reminders. So if anyone has textbooks or library books checked out, those are going to be turned in this week. Anyone in the building can turn in textbooks and library books on Thursday. You'll have a chance to kind of go take care of that. Anyone at home that has library books or textbooks, we're doing a drop off in the parent drive from 2:30 to 4. I'll be out there. Mr. Smith will be out there. Miss E, Miss Burton, so you can kind of say hey to us, wave to us. But that stuff will be dropped off and taken care of. Also, something that came out is they are going to start doing Chromebook returns kind of with exams going on. So guys in the building are going to be able to go turn in their Chromebook after their last exam. So whatever day they're in the building, that's their last exam, they can go turn it in. If you're at home, they are going to be posting, kind of a schedule for drop-offs for Chromebooks. This will be depending on if you're a senior, we kind of have to get the seniors done first because we have to track them down if they don't turn it in so they can graduate. But there are kind of dates set and there are time slots by name. Holly.
When you said turn in Chromebooks after like your last exam, does that mean state-made or teacher-made?
Any of them. So whatever your last exam is on campus, whether it's the state exam or teacher-made exam, you can turn them in. So like some of you guys may not have a state exam, so whenever your last teacher-made exam is done, you turn it in. If you have a state exam 3rd period and that's your last exam, turn it in after that one. But we kind of have to do inventory and repair things over the summer. And there's information going up on the website about it, but you'll have to kind of clean up your laptop, make sure that it's fully charged, turn in the laptop and charger. And it tells you you'll put like a sticky note with your name taped to the laptop. If there's anything that needs to be repaired, if there's a key missing, if your little mouse clicker doesn't work on your trackpad, write those things down because that's kind of how we know things need to be repaired. All right, so continuing on, we will keep doing review. So we are going to finish up. This is kind of in the middle of Unit 2 right now. So we're going to finish up Unit 2 and 3 today. And then we are going to go into nomenclature, which was our Unit 5. We did bonding before nomenclature, but we used to teach it in a different order, and I just didn't rearrange my notes. All right, so picking up with nuclear. So like I said, we stopped with half-life yesterday. With nuclear decay, there's 2 different types of nuclear decay. We have fission and fusion. So fission is going to be the splitting of nuclei. So something tends to be unstable because, there we go, thanks. So splitting is splitting of nuclei. Sorry, my board has had a mind of its own today. So this is where we tend to have a large nucleus that's too heavy to hold itself together. It's unstable, so it splits to become more stable. This is what happens in a lot of our nuclear power plants and stuff. This is how most of us get our energy, is from the fission of some radioisotope producing energy. Whereas fusion is the opposite. So think of if you fuse something together, you combine it. So this is the combining of nuclei. So this tends to be between 2 small nuclei that combine to make one larger nucleus. This a lot of times will happen with stuff like hydrogen, helium that are very small. This happens in our stars and our sun. So that's the fusion of hydrogen into helium is what occurs. This produces a ton of energy, which would make more sense for us to use if it produces more energy. However, it has to be held at such a high temperature, we can't maintain it on Earth. So fusion happens kind of in the stars and the sun, produces more energy, but it has to be at a very high temperature. So that's kind of why we stick with fission. Even though it's not as efficient, it doesn't produce as much energy, it's more stable, and we're able to kind of maintain it for a longer period of time. There were 3 different types of nuclear decay that occurred. So we had kind of alpha, beta, and gamma. With these, make sure that you kind of know what their symbols are. Their shielding, so this is kind of their strength of what they can penetrate and go through. You may also have to balance nuclear equations. So I'll kind of do an example of that with you together. So alpha particles were our helium nuclei. So that was that 4,2He was an alpha particle. These are going to be the weakest of our different types of radiation that occur. They can still be dangerous, but they're not as dangerous as the other types. With these, they can be blocked by, and I'll just put that up here. So these can be blocked by paper or clothing. So whatever parts of your body are covered by clothing, so like in the summer if you're wearing a bathing suit, the parts covered by the bathing suit are protected from any alpha particles. Then we get to beta particles. These were smaller, faster, and a little more dangerous. These were our electrons. So that's this 0, -1e. So they are a little bit stronger. These have to be blocked by metal. So even a sheet of aluminum foil can block these beta particles. And then we get to gamma. So gamma is just a type of energy. It's just a ray given off. These have the symbol of like 0, 0 gamma, which looks like a V with a tail in the middle. These were the ones that it's not actually a particle, it's just energy. These are the strongest. So these are the most dangerous. These, it takes lead or concrete to block these. So this is the stuff that is given off by atomic bombs and stuff like that, are going to be gamma rays. Or if there's a nuclear power plant that's kind of having a meltdown, overheating, unstable, it can give off gamma rays. These are the things that cause like radiation poisoning, radiation sickness, things like that. These are the ones that tend to like kill people in terms of radiation. The alpha and beta, you guys kind of get exposed to these all the time. The sun's rays have alpha and beta particles. The alpha ones tend to not harm you. The beta ones can penetrate clothing. So that's where you can get sunburnt even if you are wearing clothes. It's where they tell you to put on sunscreen before you put clothing on. Anytime you get sunburn and stuff like that, a lot of times it's from those beta rays that are stronger. Those are the ones that can cause melanoma and stuff like that. And balancing wise, because I don't think I put that on a slide. Balancing, remember everything's going to be written in that isotopic form, that AZX form. So you might have a reaction like 25682 Pb, and it's producing, and it's going through alpha decay. So that 4,2He. And we would have to figure out what it makes. So remember, whenever you're balancing, whatever you have on one side of the reaction has to equal whatever you have on the other side of the reaction. In this case, we're matching up our mass numbers should be the same on both sides, and our atomic numbers should be the same on both sides. So it would be, okay, what plus 4 gives us 256? So this would have to be 252. And then what plus 2 gives us 82? So this would have to be number 80. which is mercury. So I just kind of made up numbers. That's probably not one that you would actually come across. But you kind of get the idea of just making sure that whatever you have on both sides is balanced overall. So there are some practice ones like that on the review that I posted as well. All right, and then it kind of went into unit 3, which was our more advanced model of the atom. So still dealing with isotopes, protons, neutrons, electrons, everything. But we're kind of looking a little bit more at their behavior and their location. So one thing that was heavily in unit 3 was looking at that Bohr model, which is on the back of your reference sheet. So it kind of has this diagram on there at the top of your reference sheet page. That same page also includes our electromagnetic spectrum. So this is dealing with the types of radiation we come across. So this is on our reference sheet, and it does list the different types of electromagnetic radiation. And it goes from lowest energy to highest energy. So that's where we have our radio waves, microwaves, infrared, the visible light, UV, X-ray, and then gamma ray. So it goes from lowest energy to highest energy. And it also kind of lists out their wavelengths. So it shows you that like radio waves have the longest wavelengths of all of them, whereas gamma rays are going to have the shortest wavelengths. And remember that wavelength and frequency are inverses of one another. So the really long wavelengths are going to have a very low frequency. A low frequency is a low energy. One thing to remember with these, and I got someone coming in, these are all the same speed. So I think we kind of talked about that before, that all of them travel at the same speed, whether it's a radio wave or an X-ray, but it's the energy which can make it kind of harmful. In terms of the Bohr diagram, you're probably going to have to read this for a question or two. So remember the Bohr diagram that's given, the nucleus is that black dot in the middle. You have your different energy levels. They're listed as the n equals 1 all the way up to the n equals 6. All of these kind of lines with the dots and the arrows are electron transitions. So it shows an electron going from that higher level down to a lower level. And it gives you the corresponding wavelength that is given off in nanometers. It also tells you if it's infrared, visible light, or UV. Remember, we tend to focus on this visible light part. With these, remember, the electrons tend to start at that ground state closest to the nucleus. What happens is it will gain energy and move up away from the nucleus. It will lose energy falling down towards the nucleus. Whenever it loses energy, that's when it gives off light and things like that. So make sure that you can kind of read this. So remember, like this one right here. The dot is on n equals 6, and it's going down to n equals 2. So that would be an electron transition of n equals 6 to n equals 2. So it is going from high to low. That gives off a wavelength of 410 nanometers. How we would figure that out in what color that would be. So remember, we changed nanometers to meters. So 410, whenever we're looking at meters, would be 4.1 times 10 to the something. So when we look at our visible light spectrum, 4.1 is between 4.0 and 4.2, which are those kind of edges of violet light. So that would be a stripe of violet light. The next two, so 4.34 and 4.86, are between 4.2 and 4.9. So both of those would be blue. And then this one that goes from 3 to 2, that's 656 nanometers, would be 6.56, which is between 6.5 and 7, which would be red. So it might ask you, which electron transition is red or violet. Remember, to give off light, it always goes from high to low. It might say, okay, here's an electron transition. What color would it be? So just kind of being able to read that and go back and refresh on that. Okay. Unit 3, we also looked a little bit more at our electrons of where they actually are around the nucleus. This is where we got into our quantum mechanical model with Schrodinger. So remember, this is where we had those orbitals, those 3D shapes around the nucleus, where we put electrons in. So we had our orbitals that were the s, p, d, and f. So remember, s could hold up to 2 electrons, p could hold up to 6, d could hold up to 10, f could hold up to 14. And we write out electron configurations or orbital diagrams, placing electrons from the lowest energy level up to the highest energy level. So filling in where we're likely to find electrons around that nucleus. There were 2 ways to draw or to write electron configurations. There was the diagonal way. Some of you guys like this way, but remember, you have to be able to draw that diagonal in order to be able to use it. So we listed out our rows of the periodic table, our 1 through 7. Our lowest energy sublevel is our S sublevel, so all of those are S's. The second column started with 2. After S comes P. The third column started with 3. After P comes D. And then our fourth column started with 4. And after D is F. And we just drew those diagonals. So we go down from right to left to go through the diagonals. So this is where we would fill 1S, then 2S, 2P, 3S, 3P, 4S, 3D, 4P, and so on and so forth. So that was one way. Some of you guys preferred the periodic table way that split the periodic table up into those different blocks or sections. So your first 2 columns, so those alkali metals and alkaline earth metals, are your S block. The last 6 are your P block. The transition metals are your D block. And the inner transition metals are your F block. So this is where you could literally take the periodic table and read it like a book and fill in electrons until you got to the element you were looking for. So we would start on the first row, so we would go through 1S, then go to the second row, which is the 2S, keep going across to 2P. Third row is 3S, then 3P. Fourth row is 4S, and then the D block is, instead of the principal quantum number being the row number, it's the row number -1. So it goes from 4S to 3D. And then once it hits the P block, it goes back to being the row number, which is that 4P. So I know it's been a while since we've done that, but some of you guys kind of had it ingrained in your brains and you were doing it anyways. There's also an abbreviated version of the electron configurations. That's where we started with the noble gas before the element and only had to write the configuration of the row that the element lives on. So we'll do an example of that in a moment. All right. With those, we also did orbital diagrams. These are the ones that had like the lines or boxes, and electrons were shown as arrows. So with the orbital diagrams, we had kind of 3 main rules that we followed. We had that Aufbau principle that said we follow the order of electron configuration, so we fill those lowest energy levels first. We had that Pauli exclusion principle, which I skipped and went to the next one. That's where you can only have 2 electrons per orbital, and they have to have opposite spins. And then we have that Hund's rule, which is that second one I listed, where you have to put 1 electron in each orbital before pairing. So if we have 3 electrons and 3 orbitals, 1 is going to go in each. So let's do an example together, and I'm going to pick something slightly smaller because lead is pretty massive. Let's do arsenic. So arsenic is number 33. So if we're writing the full electron configuration for this, whichever way you go, we always fill in 1s first. We said s could hold up to 2 electrons. So then we have 31 left. After 1s, it's going to go through 2s, which will hold 2 electrons. So we're down to 29. After 2s comes 2p. P can hold 6 electrons, so that should get us down to 23. After 2p, we continue on, so the next area is 3s, which we said could hold 2 electrons, so we're down to 21. After 3s comes 3p, which can hold 6 electrons, so now we have 15 left to go. After 3p, it goes to the next row, so 4s. S can hold 2 electrons, so we're down to 13. After 4s, this is where it gets a little funky. It goes from 4s to 3d, and d can hold 10 electrons. So once it goes through 3d, I have 3 electrons left. So then it goes to 4p, and I can put those 3 electrons there. In terms of the abbreviated configuration, so remember we start with the noble gas before arsenic, which if you put your finger on arsenic, go up 1 and all the way to the right. The noble gas before arsenic is argon, so we write the symbol for argon in brackets. That accounts for these first 18 electrons, so we don't have to write all that beginning stuff. Since arsenic is on the 4th row of the periodic table, we start at 4s. So that last part is going to match from the full to the abbreviated electron configuration. If we were doing an orbital diagram, so let me pick something slightly smaller. So let me do oxygen, just because it does take a bit to draw these out. Oxygen has 8 electrons total. So if we're doing the orbital diagram for this, we go through the same process, but remember, instead of using exponents, the orbital diagram has boxes or lines with the arrows. So oxygen goes through 1s first. That can hold 2 electrons. So remember, the number of lines is half the number of electrons it can hold. So S is going to have 1 line because there's 2 electrons. Then it can go through 2s. Since it can hold 2 electrons, there's 1 line. We can put 2 electrons in there. So then we have 4 electrons left. So after 2s is 2p. We said p can hold 6 electrons, so divide by 2, that's going to be 3 lines. Oh, hang on, 2p. There's my 3 lines. And here's where we said we have 4 electrons. So 1 electron goes in each before pairing. So like I said, this is multiple choice. So you're not going to have to draw one of these. But it is very possible that you might have to identify what element one of these is. You might have one where it says which of these is the orbital diagram for oxygen. So you need to match up, does it go in the right order? Are the electrons in the right location? Did it pair things before they're supposed to be? So it is going to be a multiple choice question. So it's kind of, you have a chance to guess at it. But you can kind of say, okay, if you had something where 3p had 2 pairs and then an empty one, that's not right because you need to put 1 in each before pairing. If they happen to have the same spins, that's not a thing either. So you can kind of eliminate some answers as you go through. No. All right. This last one, this kind of went from Unit 3 into bonding. It was kind of a mix between units with periodic trends, but we still kind of lumped them together. So in Unit 3, we focused mostly on the radius trends. So remember, radius is just like it is in a circle, or in math, where you have a circle. It's from the center to the outside. Remember, atoms, because they have that electron cloud, don't have a nice defined edge. So we say that radius is half the distance between two identical nuclei. The trend for radius, so the Roboto dance was kind of your way to remember them. So radius was your left arm. And you kind of held it up and we said, okay, it increases going down and then decreases across. So the largest atomic radius should be francium, down in that bottom left-hand corner. So francium's the biggest, helium would be the smallest. And remember, that was because when you were going down, you were adding energy levels. So you went from having 1s to 2s to 3s to 4s. Going across, you were adding electrons in the same energy level. When there were more protons in that nucleus, so it pulls them in tighter. In terms of ionic radius, we looked at if it's a cation or anion. That's kind of how you can judge if it's going to be bigger or smaller. So remember, cations are positive ions that lose electrons. Anions are negative ions that gain electrons. So if a cation loses electrons, so think if you lose weight, you get smaller. If you lose cations, or excuse me, if you lose electrons, you get smaller. So those positive ions are going to be smaller than their neutral atoms. Whereas anions that are negatively charged gained electrons. So they are going to get bigger. Because since there's more electrons, the protons cannot hold them as tightly, so they can kind of spread out and expand. And then in bonding, we got to the other two trends, the electronegativity and ionization energy. So remember, ionization energy was the energy needed to remove an electron from an atom, so the energy needed to make it a cation. The general trend for this was your right arm that did that kind of awkward chicken wing. It increased going across and then decreased going down. So the largest ionization energy is helium. So that's because it has a full octet, it's stable, it doesn't want to give up electrons. And then electronegativity, remember, was kind of the same trend. So this looked at the ability to attract electrons when bonded. So this also affected polarity, which we'll get to when we deal with bonding. So this is the same trend, the same arm, where it increases across, decreases down. One thing that was different with electronegativity is, remember we said it's the ability to attract electrons when bonded. Noble gases do not bond, with very few exceptions. So noble gases do not have an electronegativity value. So the highest electronegativity is actually fluorine. That was something that trips people up because they want to put helium, but helium's noble gas. So you have to ignore the noble gases for those. All right, and then let's walk through nomenclature real quick. So nomenclature, we had different naming rules depending on what type of compound it was. So ionic, we kind of dealt with the most. They had the most rules that we had to deal with. So remember, ionic compounds are between nonmetals and metals, or cations and anions. As a general rule, we named the cation first, and we didn't have to change the name of the cation. We kind of named it as is off the periodic table. And then we named the anion and tended to change the ending to IDE if it's off the periodic table. So like fluorine becomes fluoride. If one of them was a polyatomic ion, we have to name the polyatomic ion as is on our polyatomic list, which remember is on your reference sheet as well. So a lot of our polyatomics ended in ITE or ATE. We don't change the ending of those. We leave them be. If our cation was a transition metal, remember transition metals a lot of times can have multiple charges. If that's the case, we have to have the charge written as Roman numerals in parentheses after the metal name. So that's where we had like iron 2. So that we know that whenever we're writing that out, it has a +2 charge versus a +3 charge. Exceptions where you will not see these are silver, zinc, and cadmium. So these are ones that only have one possible charge. Silver is always +1. Cadmium is always +2. Zinc is always +2. So kind of a way to remember that, if you remember, we have like our group A elements and group B elements, and they have the Roman numeral and the number and the letter up above it. Silver is in group 1B, so it has a +1 charge. Zinc and cadmium are in group 2B, which is where that +2 comes from. So that's kind of a way to remember it. And whenever we're writing formulas for ionic compounds, because they do have charges, we have to crisscross those charges to get our subscripts and then reduce if needed. So that's where we might have something like, let's do copper 2 sulfide. Or let's do copper 2 sulfate. There we go. So we can throw a polyatomic in there. So we'd say, okay, copper is Cu. It tells us here that it is a +2 charge. Sulfate, anytime you see that ITE or ATE, you know it's a polyatomic off your list on your reference sheet. Sulfate is SO4 with a -2 charge. Whenever we crisscross, those 2's are going to cancel out. So that's just going to be CuSO4 would be our overall formula. So I know it's a while since we've done that, but it's still the same rules we've been doing. Sorry, I've been losing my voice since yesterday. Then we did our molecular compounds. So remember, these are going to be like nonmetals and nonmetals together. So with these, we did not have to deal with any charges. So we're not crisscrossing or reducing. Here we use those metric prefixes to tell us what the subscripts are, to tell us how many of each atom we have. So prefixes are for nonmetals only. And then we also did hydrates. So hydrates are one of those kind of specialized compound types. There's not too many of them that exist. But hydrates are ionic compounds that have water molecules attached and bonded to them. So whenever we're naming these, we want to name the ionic compound using our ionic rules. Then indicate how many hydrates, how many waters are attached by using our molecular prefixes. So if it was like 2 waters attached, it would be dihydrate. For writing the formula for these, we write the formula of the ionic compound, then whatever number that prefix is indicating, followed by waters. And then we also had special naming rules for acids. Bases we named as is. So we didn't have any special rules with bases, but acids we had special rules with. Remember, acids are going to start with hydrogen. So it's going to be that HX form where it has hydrogen and then some anion followed behind it. Depending on the ending of that anion is how we name these. So if the anion ended in IDE, so this is going to be stuff off the periodic table, and the polyatomic cyanide, it's going to have the prefix of hydro, the main part of the anion name, and end in ic acid. So if we had HF, F is fluoride, so this would be hydrofluoric acid. If it ended in ITE, so that's going to be some of our polyatomics, that has no prefix. It has the main part of the anion name and ends in us acid. So that would be something like HClO2. ClO2 is chlorite, so this would be chlorous acid. There's only so many polyatomics that end in ITE, so that's probably the least common rule you come across. And then we have our rule that uses ATE. So these are our polyatomics that tend to have more oxygens. Remember, this is very similar to that first rule, but it does not have a prefix. So this does not have a prefix. It's the main part of the name, ends in ic acid. So if we had like HNO3, NO3 is nitrate, so that would become nitric acid. And like I said, bases didn't have special naming rules. We named them just like any other ionic compound. And I think that's my last one today. Yep. So that's where we're stopping today. Kind of to go through stuff. Remember, I do have that review posted. That kind of has, it's all short answer questions for the review, mostly. But it kind of makes you go through, make sure that you're comfortable with concepts, even if you don't do it completely. If you scan through and you're like, I'm not sure if I know how to do this problem, let me try it and check it, things like that. That can help you prepare. Remember, during this time, you can work on any missing assignments that you have. If you need to do the test or quiz remediations for reactions, moles, and stoichiometry, those are posted. So if you're not feeling happy with where you are right now, those are things that you can do to kind of improve your grade. Remember, your final does count as a test grade, so it's going to average in with your other tests. So it's not going to be one of those things that unless you bomb it, it's not going to cause you to fail. But it could mean the difference between you're sitting at a C and you want a B. So it could kind of give you that little extra boost. Same thing with the remediations. If you completely bombed a test and got like a 30, this is a chance for you to get a 60. That's definitely going to bring you up a couple of points. So kind of use those things to your advantage. You guys have the rest of the period to work on what you need to. And I will see you guys tomorrow. My guys at home, I'll stay logged on if you have questions, but you're welcome to log off if needed.